So I wanted to finish off something we were doing last time about left-derived functors. So I claimed that if we computed them by taking projective resolution, well, we showed that that was well-defined and it was a functor, but we also claimed it was natural. So if I had two short exact sequences, for each of them I get a long exact sequence, and I'm supposed to get a map of long exact sequences. So I wanted to indicate what you have to do to check that. I was suggesting it would be an exercise. So let me kind of sketch what has to be done. And then I want to say more about Tor. And then we want to move to right-derived functors, in particular to Ext. Right, so remember, I'll restate the proposition. I think it was a proposition. So more on the left-derived functors, and plus we'll talk about right-derived functors. So the situation was the following. And we proved most of this last time. So if I had f a functor between module categories, you can do this more generally, but we're focusing on module categories for now. So if this is a, let's see, right exact functor, so meaning it takes short exact sequences to right exact sequences, but maybe it's no longer exact on the left. So the typical example was tensoring with a bimodule. If this is a right exact functor, then applying f to a projective resolution to projective resolutions of modules, that will produce new complexes, and then I can take homology of those. So applying f to projective resolutions of modules and taking homology gives new functors, so-called left-derived functors. So they're denoted Li if I do the homology in the ith place. Goes from R modules to S modules. Such that for such that given a short exact sequence, let's say it's x prime, x double prime, we get a long exact sequence starts out as what the values of f would be. I think I forgot to start the video. I just started the translacja. So this is the proposition from last time. I'm just restating it. So given a short exact sequence, I apply my right exact functor. I get a right exact sequence. Maybe it's no longer exact on the left, but the left-derived functors correct that. So the first one appears here. And it continues with the second derived functors, and so on. So I'll call these maps, these are these connecting maps, deltas. And, so this we proved last time, and we have naturality. So, and given a map of short exact sequences, so here's one short exact sequence, here's another one, and a map of short exact sequences is a commutative diagram like this. So I'll have a long exact sequence up here and up there. Each LIF is a functor, so it will take this map to a map. And I want to know that the squares, that it commutes with these connecting maps. So we got a map of long exact sequences in the sense that if I look at the connecting map from the ith, well, I have the ith left or right functor. Since it's a functor, it will map x double prime to y double prime. I also have the connecting map and this commutes. Okay, so this commutes. And so last time we justified everything. We constructed the long exact sequence except this naturality. And I just want to hint at how to check the naturality. So let me remind you how you got the long exact sequence. So recall, last time we did everything. Up to checking that this last square commutes. To check that it commutes, let's remember how we construct the long exact sequence. So recall, to get the long exact sequence, to get the two long exact sequences, we choose projective resolutions of x prime and x double prime, and then we glue them together to get a resolution of x that fits into a short exact sequence of complexes. And we'll do the same for y and y prime. So to get the long exact sequences, we choose projective resolutions p prime to x prime, p double prime to x double prime, and those choices, what do they do? They're giving which we use, from which together with the horseshoe lemma, gives short exact sequence of resolutions. So there's the resolution here. It will embed into some new resolution we get like this. Where the terms of this middle thing are just the sum of the two terms, but the differential has some upper triangular form. So the nth term of the middle complex is the sum of nth terms from the outer complexes. And the differential has the form d p n, let's say d, let's say so that's the differential on p prime, that's the differential on p double prime. And then there's this extra term phi n, where phi n is a map from what? From p double prime n to p single prime n minus 1. And we constructed that when we proved the horseshoe lemma by using the lifting property for projective modules. And I could do this for the short exact sequence x prime x, x double prime, and I could also do it for the other short exact sequence. So likewise, we choose projective resolutions and then we get so we get a short exact sequence of resolutions of y prime, y, and y double prime, where the middle term is the sum of the outer terms, and the differential is of the form d prime y, let's say dy prime, dy double prime, and here there's some psi n, where psi n goes from q double prime n to q prime n minus 1. Okay, just the same thing. But now we want to claim, the claim is now that this map of short exact sequences give them names. It might be useful when you really work this out in detail to have names for all of the arrows involved. We know from this lifting lemma about projective resolutions that this map f prime maps to, lifts to a map between the resolutions of x prime and y prime, and similarly out here. And now we're going to want to use the lifting property for projective modules to lift compatibly to a map of resolutions of x and y so that everything commutes. Okay. So we know, so by the, I don't know, map lifting lemma, I don't remember what it was called. This map and this map from x double prime, y double prime, these lift to maps of resolutions. call them. It's P prime to Q prime. That's F prime dot. MP double prime, F double prime dot. So that we know. And those lifts are unique of the homotopy. And now the claim is that we can inductively construct a lift of the map from X to Y to a map of resolutions like this, such that altogether we get a commutative diagram of the following form. So I'll have my short exact sequence of resolutions for the X short exact sequence. And I'll have lifted my maps between the short exact sequences to maps between the short exact sequences of resolutions. This will be F dot, F prime dot, F double prime dot, like this. And now if you take the long exact sequence here and here, you'll get these commuting long exact sequences as we claimed. And because these lifts are unique up the homotopy, the maps in the vertical direction are well defined. Okay, so how do you do this inductively? Don't want to spend the whole time on this, so I'll just, it's very similar to what we already did. So I'm just going to indicate what you have to do. So the idea for the inductive construction is the following. Is to take, is to make the nth map of resolutions from P prime to Q prime. So where does it go? It goes from this sum to this sum. So we're going to write it as some kind of matrix. So we're going to assume that it's of the form that's compatible with the differentials. Remember these had these upper triangular differentials like this. So we're also going to have this map of upper triangular form to construct inductively. So it will look like the following. Right. So we already have a map from here to here. That was F prime. I'm just going to put that in here. And I already have a map from here to here. That's the F double prime. But in order to make everything work well with these upper triangular differentials, I'm going to have to include a cross term, which goes from here to here. So this will be, I'll call it gamma n. So this is where gamma n is a map from p double prime n to q prime n. Okay. And to see what gamma n should be, in order for this to, in order for gamma n, in order for this collection of fn's of this form to form a map of complexes, and for this to commute, some relations must hold. So you can work out what the relations are. And you can show that using the lifting property for projective modules, you can always solve for gamma n inductively. So it will be similar to the way we proved the horseshoe lemma. So using the lifting property, for projective modules, solutions to these relations for gamma n, these will exist inductively. So that's now kind of a road to what you have to check as an exercise. Okay, so we want to do something new today. I'm going to leave the rest as an exercise. Maybe we can even talk about it in the seminar if we have time. But it's very similar to the proof of the horseshoe lemma. There's also details in Weibel's book, although personally I find it easier to just think it through than to read what he writes sometimes. But it's probably in other books as well. It must be. Okay. So that's wrapping up from last time. The new thing I want to do today, what was our main example that we gave of left to right functors? Well, we started with the right exact functor of tensoring, and then the left to right functors were Tor. We computed examples in the seminar. Last time of group homology, defined as this kind of Tor. And Tor has two variables. So we wrote last time Tor I, R, X, Y. I don't even remember which one we did in class last time, but I could think of, X as fixed and Y as variable, or Y as fixed and X as variable. And you might worry that if I try to compute this by, say, fixing X and resolving Y, the variable Y, will give a different answer from fixing Y and resolving X. Okay. So question. Does it matter? Well, it doesn't matter. This will be the proposition. Okay. So this was our example last time. This was computed by resolving one of the variables. Which one? So it doesn't matter. So this is the proposition. This is called balancing Tor. Balancing either on the left or the right. Right. So it says the following. So given a projective resolution of x and of y, p dot to x, q dot to y, we get, we have the maps of complexes. So one thing I could do is I could tensor together the two resolutions. Remember how I take the tensor product of two complexes, I form a double complex, and I take its totalization, its sum totalization. In the proof, we'll write that out explicitly if you don't remember exactly how it works. We also have a map from p dot as a complex to x thought of as a complex in degree 0. And that gives a map from p dot tensor q dot to x tensor q dot, which is the thing you would use to compute Tor if you were resolving the variable y. Similarly over here, I have a map from q dot to the complex y sitting in degree 0. So I have a map of complexes like this. And the claim is that these two maps of complexes are quasi-isomorphisms. They induce isomorphisms in homology. Okay? In particular, it doesn't matter when you're computing Tor whether you resolve y or whether you resolve x. So in particular, to compute Tor, you can resolve either variable. Or both. If you're very enthusiastic, you could resolve both and write down this complex. Okay, so the proof actually depends upon a lemma, which is maybe of independent interest. And there are two versions of this. There's a kind of tope plus version and a tope product version. We'll use the tope product version later. Let me just give the tope plus version. So this is called acyclic assembly lemma. I need to start writing it out before I give the correct statement, because I'll confuse rows and columns to begin with, and then I'll fix it. So given, let's see, given a double complex, of the form so it's going to be kind of upper half plane. So there's a horizontal differential. The first number should number the row, so it should look like this. This is the first row. Still first row, but 0th column. First row, and so on. So it can go up in this direction or to the left and right in any direction, but below this, it's all zeros all the way down. Okay. So given a double complex like this, with, let's see, with, to think, exact either rows or columns. So which one do I want? I'm going to fill this in, and we'll kind of see in the proof which one it will be. Okay, so I always work this out when I need it. So let's call this x double dot. Tot plus x dot is acyclic, meaning has no homology. So the homology is 0 everywhere. And similarly, if this one is rows, then the other one will be columns, or conversely. So likewise, is just what we get by rotating this one like this. So likewise, if a double complex that looks as follows, so it's like this with zeros over here. By the way, I don't think there's universal agreement on how one should write double complexes and which direction the arrow should go. It's always a convention. So people will talk about upper half plane or lower half plane or right half plane and so on, and you have to know in which direction the arrows are going to make sense of that. Okay, so anyway, this is the one I mean. Okay, so if I have a double complex like this with exact, we'll check in the proof, we'll see which one it is. So if that one's rows, this one will be columns, or the other way around. One is just kind of rotated from the other. Then tau plus is acyclic, meaning quasi-isomorphic to 0. Okay, so let's try to prove it, and we'll see which one is rows and which one's is columns. So let's try this one. So take the upper half plane case. And, you know, it's symmetric for, the situation is symmetric for translating left to right. Okay. So I can focus on a single degree. and whatever argument I give in that single degree for homology of tau plus will apply to all degrees by translation. So I'm going to take degree 0. Okay. So by translation, enough to see that H0 is 0. So let's suppose we have a 0 cycle, and we're going to see that it's exact. So suppose, let's call it x. So what is this? It's x0, 0 plus x 1 minus 1 plus up to xp minus p is a 0 cycle. Okay. So let's write down what that means. And remember, when we form tau plus, I have to choose either to alternate the signs on the horizontal differentials or on the vertical differentials in order to make the squares anticommute, so that when I take tau plus, the differential will square to 0. So I think I'm going to choose for the vertical differentials to vary in sign. So then, but those two complexes will be isomorphic, so that choice doesn't make any difference. So this would be the following. So I would have d horizontal applied to x0, 0. I would have d vertical applied to that, but that's already 0, so there's no term there. So plus, and then I would have the d horizontal applied to x1 minus 1 minus the d vertical applied to x1 minus 1 plus, and I would do d horizontal applied to x2 minus 2 and so on, all the way down to d horizontal applied to xp minus p plus minus 1 to the p d vertical xp minus p. Okay? And let's look at this last term where it ends. So if this is a cycle, this whole thing has to be 0. And some of these terms live in the same components, so they'll add up. So let's look at these last two and see where they live. So I have xp minus p, xp minus 1 minus p plus 1. This is what? X p minus 1 minus p. This is d horizontal. This is d vertical, d horizontal, like this. This is x p minus p minus 1. So right here, if this is going to be 0, this term can't be canceling with anything else, because all the other stuff is down here, so it doesn't contribute to this term. So this implies that d horizontal, just by itself, of xp minus p equals 0. The other term, this dv, gets added up with d horizontal of this term. So I don't know that this by itself is 0, but I do know that this is. Okay. So what that tells me is if the rows are exact, then since this is 0, it must be not only a cycle, but also a boundary. So the correct statement is exact rows here. And here, this one is exact columns. Okay. So now, since the rows are exact, assumed as exact, there exists something here in xp minus p plus 1, which maps under D horizontal to xp minus p. Okay? And so I can modify my original cycle by this boundary and get rid of this last term. So thus, this original cycle is homologous to x minus this boundary, which is dh, which is d of this thing that has a single term, xp minus p plus 1. And this thing will just look like, it only modifies at the very end. It will modify this term, but there will be no p term, because I kill it by subtracting it off here. Okay? And so proceeding inductively, I can repeat. This is now a new cycle, but shorter than the one I started with. I repeat, and eventually I'll see that the whole thing is a boundary. So by induction, we find that x is a boundary. Okay, so that works. And for the other statement, this one should be exact columns. The proof is exactly the same. You just have to rotate this diagram. So for the other case, rotate this argument. So this is a simple observation which actually comes in handy often, and we're going to use it to prove this. Okay, so now let's do the proof of the proposition. So proof of balancing Tor. I'm saying the difference between these is exact.
Yes. So,
and therefore zero in homology.
So doesn't that hold for every element homology, not the zero elements? I mean, no matter x is what, x must be homologous or something like this. I mean that
in a different complex. I mean, the point of this is, yes, I can always add on any other exact term, But what's good about adding on this particular exact term is that it made the cycle shorter, and I can repeat inductively.
But I mean, you don't need x minus d of something. You just need d of something.
But I'm constructing that something inductively. I haven't done it yet. I've only subtracted off the part which contributed the tail of my cycle. So I got rid of this term, and then I modified this term. And now I have to repeat. I have to get rid of that term and modify the next term and go all the way down. So in the end, it will be true that x will be d of something, but I have to construct that something inductively. And I've only told you how to get the induction started. I hope it's clear how to continue. Okay, so proof of balancing Tor. So let's remember how we construct the tensor product of two complexes. So to construct this, we form a double complex. Which looks like the following. So I'm going to take the indices on P and Q to be, well, rows and columns. So this will be P0, Q0. This is 0th row, so here I'll put Q1. This will be first row, so P1, Q1, P1, Q0, and so on. So this double complex lives in this corner, and so actually it's of both of these forms. And moreover, so we form this double complex like this, and we take TO plus. But I claim that both rows and columns are exact, almost exact except on the ends. Yes, okay. So I have this double complex, and we take let's augment these. So what is this? This is Q0 tensor the projective resolution of x. Right? So down here I'll have x tensor Q naught. Here I'll have x tensor Q1, and so on. Over here, if I look at the rows, this is P0 tensor the resolution of y. So over here, I'll have P0 tensor y, P1 tensor y, and so on. Okay. So if I look at this one, together with this augmentation, here, the columns will be exact because the sequence x, P0, P1 is a resolution, therefore it's exact, and I'm tensoring with something projective, and tensoring with something projective is exact. Similarly here, the rows will be exact because they're tensoring a projective module on a resolution of y. Okay. So note the two, I don't know what to call it, like this. So the left-hand augmented double complex has exact columns since the columns are resolutions which are exact tensor projectives, and tensoring with the projective is exact. And likewise, the rows of the upper augmented double complex are exact. And so their sum totalizations, either here or there, are acyclic. So both tot pluses are acyclic by this acyclic assembly lemma. And why is this relevant? We can interpret what these totalizations are in terms of these maps, which I've erased. But if I take this totalization, I see in it, if I just totalize this part, I would get P tensor Q. And if I just totalize this part, I would just get the complex itself, X tensor Q. And then I would have a map from this totalization to this totalization. I could take its cone. Okay? And I claim that it's easy to check the totalization of this whole thing will be the cone of totalization of this and totalization of that. So tot plus of the left-hand double complex well, up to a shift. This will be the cone of P dot tensor Q dot mapping to X tensor Q dot. Okay. And so since this is acyclic, the cone is acyclic, but the cone is acyclic precisely when this is a quasi-isomorphism, because I get a long exact sequence and homology of this, this, and the cone. Okay. So this map is a quasi-isomorphism. And likewise, tot plus of this upper double complex with a shift is nothing but the cone of the other map from P dot tensor Q dot to P dot tensor Y. Because when we constructed the cone, we saw that there was a long exact sequence in homology between the first thing, the second thing, and the homology of the cone. If that's 0, that means in each degree, the map on homology must be an isomorphism. Okay. So this is a quasi-isomorphism. And that's what we wanted to prove. That these two different ways to compute the tensor product were quasi-isomorphic. Okay, that took a little longer than I expected, so we won't get so far on right-derived functors, but we can begin talking about injective resolutions. And the story for injective resolutions is dual in a precise sense to that for projective resolutions, so we'll be able to go a little faster. So let me start by what is an injective resolution and why they exist. We explained this a bit in the seminar. I left it as an exercise on the day we had an informal seminar. Now I'll give some more details. So definition, so now we'll talk about injective resolutions. So first let's recall what is an injective module. So injective modules, so a module I, let's call it, in our mod, is injective if for all inclusions x into y, and maps from x into I, we can extend this map from x to y. Okay. There exists this making this commute. So this injection is given, this map is given, and I can extend it to f tilde. That's the definition. And we checked that Q mod Z was injective as an abelian group. And we saw in the seminar that for any abelian group A, it injected into the product of QZs, which is also injective. Products of injectives are injectives. It's easy to check because the property of B injective is about mapping into it, and you know how to map into products. That's the universal property of a product. So here the product is over all maps. Like this. Okay, so we checked all that before. And so now here's the claim, lemma. How do we construct, given a module over a ring, how do I embed it into an injective module? So we know how to do this now for abelian groups. So in general, there'll be a few parts to this. So one is that, so fix a ring. I want to find the analog of Q mod Z. So the analog of Q mod Z, I'm going to define it. I'll call it, I guess, I sub r. I have to give it some kind of name. So this is going to be homomorphisms from R into Q mod Z. Okay, so this will be an R module just by acting on the source. So the claim is this is an injective R module. This will actually be easy. We'll realize this as the image of this injective thing under some right adjoint functor, and right adjoints take injectives to injectives. B, X will embed into a product like this of IRs. So this will be embed X into an injective. And now, to get an injective resolution of X, so a complex whose terms are injective and which is exact. So repeating this on the co-kernel, so given this injective, we have a co-kernel. Let's call it coq 0. Okay, so that's a short exact sequence. We have, I can repeat on the co-kernel. I can embed that into the same kind of thing. And inductively, like this, we get an injective resolution as follows. So X will embed into something that I'll just call I0. So it injects into some injective, and then there's another injective and another. This is a complex, and it's all exact. And it's traditional to, we were indexing projective resolutions with lower indices. Here, these are upper indices. We also make them positive. So this is cohomological grading. And the projective resolutions were homological grading. It's just a convention, but this is traditional. Okay. So this is actually interesting in some ways. On the one hand, this is a totally natural process. There's never any choices involved. I always know exactly what the injective module is into which my module injects. This is unlike that of a projective resolution, where I had to choose generators in order to surject onto it from a free module. So there are no choices involved. On the other hand, this thing can be huge. I mean, Q mod Z is it's a big abelian group, and there might be a whole lot of maps from X to Q mod Z. So this product also may be over a very large set. So this is some very big abstract thing, but it's also natural. And that tends to happen. Anything that is kind of very natural and which involves no choices is very big and hard to understand. Okay, so proof. It's all about the following observation. It's just the co-kernel of this injection, so that this is exact. And then I take the co-kernel again, and I embed that into an injective module and continue. Okay, so proof. The forgetful functor from our modules to Z modules, which are the same as abelian groups. Normally, I just think of it as just forget. But I can also write it as well, I could tensor with R over R, and that does nothing. Yes? So it's isomorphic to this. And so because the forgetful functor is given as tensoring with a bimodule, so I could think of integers acting on the left and R acting on the right of R, it's given by tensoring with a bimodule. Not only does it have a right adjoint, I know what the right adjoint is. We have a right adjoint which is what? It's Hom over the target ring with out of the bimodule. It has a right adjoint. Okay. So this is the basic observation. Moreover, right adjoints between module categories preserve injectives. This is something we checked, I think, in the seminar when we introduced injectives. Right adjoints preserve injectives. So, this thing, IR, is exactly applying a right adjoint to an injective. So this is injective. Okay. Next, I want to get an injection of X into this product. So for B, let's start with injecting X into the product of QZs. I can just forget that X is an R module and remember that it's an abelian group. So we have X into the product of Q mod Zs, product over maps, X to Q mod Z. So that we already know. And this is in Z modules. Okay. So now I can apply my right adjoint functor to that. Right adjoint functors preserve limits. In particular, they preserve kernels, so they preserve injections. Okay. So since right adjoints preserve injections, we now get Hom Z R X injects into Hom Z R product but we're humming into a product, so that's the product of the Homs. And what is the Hom? It's Hom from R to Q mod Z, so that's what we called IR. So here we get an injection from Hom R to X into this product that we're trying to understand. That's almost what we want. We want the injection from X. Okay. So now compose with the map. Well, what was this? This was forget, and then take the right adjoint to forget. So there's a natural map here. This is the unit of the adjunction. And we can write down what it is explicitly. It sends an element X to, it has to give me a homomorphism. What homomorphism will it be? It will send a ring element to that ring element acting on X. And that's additive in X because multiplication distributes over addition for a module. It's also additive in R because of what a module is. So it sends an element X to a homomorphism, and it's you also have to check that this is R linear, but this will follow from knowing that it's a unit. Okay, so I have a map like that, and I claim that map is an injection. And so when I compose these two, I'll get the injection I want. So note this ladder map. Is an injection. Because suppose X went to 0. That would mean this map, which sends R to R times X, would be 0 for every R. So if it's 0 for all R, in particular 0 for R equals 1. It would be 1 time, it would be X, which is 1 times X, equals 0. Okay. So this map is injective, and that map's injective, and so the composite embeds X into this product. So the composite composite is the injection that we need. So this is a desired injection of X into an injective module. I just needed it to be some injective module, but this one is very natural. Okay, so there it is. And part C is really just a comment that I can iterate this process. Once I have an injection into one injective module, I take the quotient and inject the quotient into an injective module and continue like that to produce an injective resolution. They are just some injective modules. In this case, they're very specific injective modules, but for a general injective resolution, it would just be a long exact sequence like this, where all of these were injective. It's a fact, an interesting fact, that for modules, there's always a natural choice for this, given by this construction. I can always, given any module x or x prime or whatever, I have some natural injector module into which it injects, given as this product. In some more exotic setting, maybe there's not a natural choice. So I'll give a definition. A dual to what we did before for left-derived functors, and then I'll end with that. Definition, proposition. Because there's a definition and then a proposition telling you that it's well-defined and has good properties. So given a left-exact functor, between module categories, I'll call it G. The other one was F. Maybe I'll reverse the names of the rings as well, because sometimes they come in adjoint pairs. So given a left exact functor like this, applying G to injective resolutions of modules, and taking, now I would say it's cohomology because I've traditionally liked to index injector resolutions in this positive way. We get right-derived functors. R, I, G. And they have the expected properties. So these take short exact sequences. So if I have a short exact sequence of this form, I get to long exact sequence. So what's it look like? It starts out as G. Remember, G is left exact. So it will start out with a left exact bit. So it'll be G of x prime, G of x, G of x double prime. And then the first derived functor, R1G x prime, R1G x, R1G x double prime, R2G x prime, and so on. And it's also natural in maps of short exact sequences. So I'll get maps between long exact sequences. Okay, and so this is proved. Maybe we'll have time to do some in the seminar, but it's proved in basically the dual way that we proved the left-derived version, just using injective resolutions instead of projective resolutions. So you show that maps of modules extend to maps of injective resolutions using the lifting property for injective modules. You have something like the horseshoe lemma. So given a short exact sequence of modules, you can construct a short exact sequence of their injective resolutions, and so on. And the most important example and I'll stop after this. The most important example is if x is, let's see what, if x is a maybe S R bimodule, then if I hom over S from X, that will take an S module to an R module and this will preserve injections and, in fact, exact sequences on the left. That's what we proved when we introduced injective modules. Okay, so this is left exact. And the right-derived functors are called the X modules, or the X functors. And next time we'll study these more carefully. Okay, but there's the definition. So we'll stop there for today.